All right, welcome everyone. We probably will get a few more people joining, but let's go ahead and get things started. Today we're going to get an overview from Jamal related to the P4TC and how that ties into the OPI. So Jamal, if you want to get started, that way we get as much time as possible for what you wanted to present.
Thanks, Mark. Okay, so I'll share my screen. That is, so I'm not sure what format is preferable here, but I'll go over the slides and interrupt. I have only about 10 slides because there's a lot of detail, but I have backup slides if someone asks a question and I have to clarify something. I'll put it on big full screen here. And so I'll go over some introduction and motivation for this work, high-level overview of the development, how one would go about developing a P4TC friendly program and how they deploy it. And eventually I'll tie to, on one of the last slides, I'll tie to how it fits with OPI. And I'll provide a status update of where we are today. So motivation, really, I mean, this started, this work was inspired by Nick McKeown at Intel, is to grow network programmability ecosystem. We've been talking about this since about 2015, initially introduced by the NVIDIA folks. A guy by the name of Matti Kadosh showed up one day at one of these Linux networking conferences, and he said he wants to do this thing called P4, and we laughed at him. And he kept coming back, so that's how it started. And a few years later, now we're doing it for real. So the three constructs. One is the data path definition is done using P4. Then it's implementing using the Linux kernel and including both software and hardware. And one of the main goals of this is to reduce developer dependency. So you don't need a genius who knows eBPF in order to write this code. You start with your P4 program, you run it through a compiler, it generates code, and after that, it's an operational.
Jamal, we are still seeing agenda slide. If you meant to proceed to the next slide, we are not. Okay, now we see it. Okay.
Is it?
Yeah, now it's okay.
Should I be sharing the whole window instead? I was just sharing a tab.
No, we're good now. We're good now. I think you can see motivation slide now. Yeah.
Yeah. So the motivation essentially is you start with P4. That's where and then you go through a compiler and it generates the necessary artifacts for the control data path, and the traditional way is also generate the binary blob that the hardware needs. And I was just stating that this does not require a lot of coding skills. So we are trying to cater for both folks in the P4 world who don't want to know anything about the kernel, as well as kernel folks who probably don't want to know much about P4. So did my slides move there, Vipin? Or I'm now on the next slide, which says why P4.
Yeah, we can see that now.
Right. So why P4? I guess the obvious fact is it's the lingua franca, if you want to say that, if you want to call it that. There's nothing else out there in the industry, as far as I know, someone could correct me, that is capable of describing data path in a format that's agreeable to many folks. I mean, I know there's the Broadcom variant of this, but that's Broadcom specific, and there's not much information out there. The other motivation is I believe people are now using this to define P4 to define data path description. So if I'm a consumer, I'll give you a P4 program as my specification to a NIC vendor and just make sure get this to work for me. My understanding is that how Dash operates. I'm not involved in that. My understanding is also as well as big organizations like Google, they specify the specs as well through P4 programs, and they want to make sure the vendor gets that to work. The other motivation here is with P4, it's very clear that if you go to different organizations, they all have slightly different needs for what their network is. So Conway's law applies, means I can start with a P4 program to describe my data path based on my way of thinking and essentially deploy it using this mechanism. And I don't have to deal with any standards bodies or have to appease somebody else to accept this upstream, for example. Right, so why the Linux kernel? Okay, I may be exaggerating a little bit there, saying if it beeps, probably is running Linux. But it's the mother of all networking infrastructure. You may not run the Linux kernel for your networking infrastructure, but you will be probably booting Linux kernel. Gives us a singular API with the assumption here that vendors are going to produce drivers that interface with P4TC. And you have the same consistent interface. So you can write your P4 program, run it on software. And when you're ready, with a toggle of a button, it runs on hardware. Right, that is the goal. So going into detail of data path definition, we use it to generate both the data path for the software and hardware and interfaces for the control plane. And there is, in theory, as this diagram shows on the right here, that there is functional equivalence between what runs in the software. If you decide you want to run it in software, you put an input X, you get an output Y. If you decide to run it on the hardware, you put an input X, you get an output Y. The scale may be different, the implementation may be different, but the functional equivalence exists. The control plane, there may be capacitance or impedance mismatch between what's in the data in your implementation of the hardware. You may be using different types of tables. We don't care about that. The abstraction is the P4 objects. So we send you the P4 object, we give you its ID, and you take care of how that maps to your hardware. So that's what's functional equivalence. In Linux, in the Linux kernel, if you're going to offload through the kernel, this is expected. It's expected that I should be able to run and test this in software, in the kernel, and be able to use the same semantics, let's say through TC, to offload. And there's a lot of experience built into TC. There's all kinds of. It's always easy to write code day one, and it's looking good. LEDs are flashing, sounds coming out of the box. I think the value add in TC is many years of deployment and experience in fixing corner cases, etc., that we'd like to take advantage of. There are some challenges, but those are experiences from the past that we want to learn and not repeat when we are doing P4TC. So ideally, you can test on a software container, VM, and when hardware is available, you offload it. We have total kernel independence. So if I write a P4 program that does, I don't know how many people are aware of the calc program, I don't have to push anything to the kernel, right? I can use my kernel as an endpoint calculator and I'll send it 2 operands and an operator, and it gives me back a response. And it's ridiculous, but it shows the power of this. And unlike other offload mechanisms that exist today in the kernel, for example, TC Flower, or if you've offloaded U32, the other mechanisms, anytime you create a new program that has new headers, you have to change the kernel code, you have to change user space code, you have to go through, at times, up to 2 years or more before that code shows up in an enterprise system. We're going to learn from previous experiences. We are learning, I should say. For example, there are a lot of gotchas with TC Flower in terms of certain workloads, I'm sorry, in terms of scaling, not just from the data path, but also from control plane, right? Because it's per interface approach. We want to make it P4 architecture independent, so you should be able to run PSA or PNA. I'm not sure how much people know about P4 in this audience, but we are focusing initially on PNA, I'm sorry, but there is nothing that's stopping someone from using PSA or inventing a new architecture and running on top. We want vendor independence in interfacing, so there is no need for. I'm a kernel guy, a kernel bigot, I would say. So we don't want to go out to call some APIs that the vendor introduces, and then some other vendors has a slightly different API. A single API, that's the kernel. We also don't want to do the cumulus foo, is what I call it. made popular by Cumulus. They definitely not invented by Cumulus, where you're listening to Netlink events and then calling some sideband hardware offload, right? This is all done through the kernel. You run your P4 program. So what you do is you create your P4 program. You may have some target constraints. The traditional path when you put a P4 program is you run, the compiler will have a vendor backend, which then creates a binary blob that you load into hardware. So this is the well-known approach to P4. What we're doing is we're adding a P4TC backend. This code exists, by the way. You can go and download it today. It's not by any means 100% complete, but it's there. It's usable. You then generate an eBPF program for the software data path, and you generate a bunch of policy scripts that are, when loaded into the kernel, they manifest the P4 program in the kernel. So this is just policy through TC. This is an eBPF program. So you, assuming you don't have hardware, you're just doing software, you get your eBPF program, which then gets compiled into an eBPF binary, which then gets loaded through BPF system call through TC. And in addition, you have to run, typically this is just one script the compiler creates, but I just separated it into multiple just to show the distinction of the different stanzas within that script. And you load this. P4 is a command called TC P4 template, loads it, puts in the kernel. In addition, the compiler generates what we call an introspection file. And the goal of this is to avoid rewriting any user space code as well. So this is a JSON file that prescribes what is acceptable for a control plane API. And I'm going to show, if we have time, I can show some more details on that. But basically, there are several, everything in green is what's generated. If you have hardware offload, you will generate this green blob. If it's only software, you generate an eBPF program, a bunch of scripts, and an introspection file. You load them, and then you're ready to go. Now you can go into the runtime. So I left that diagram here just to show the different pieces. So there's the P4 template script, which is this piece here. There's the eBPF program, which could be loaded if you're familiar with eBPF, either at TC level or at XDP level. There's the vendor binary blob, which gets loaded there. At runtime, if you're using the TC utility, you don't have to. You will then introspect this JSON file, which will describe to you all the acceptable parameters for the control plane. And you may choose to just run it on software, in which case you only update the kernel tables or objects, I should say. And if you want to do an offload, then you would go straight to the hardware, or you could do both. And there's a scenario where you could say, please try to offload it. If it fails, just make it run on software. So that's the runtime. And you could put your own control plane here. We are providing the TC IP route 2 TC infrastructure for allowing that. Packets come in. If they're processing hardware, then the software never sees them, depending on what your policy looks like. If not, there's an exception path through software, which, depending on how you generated your code, you may just want to run it only on XDP. You may want to run it on both XDP and eBPF, for example, the parser may run here, and then you run the rest of it there. Right, so software data path essentially runs here with consultation of all the P4 objects that sit in the P4TC kernel domain. There's something called kfunc, if people are familiar with it. I can go into a lot of details about this if it's necessary. I wasn't sure it is necessary for this meeting. But you basically have a sideband lookup to this. And what we are taking advantage is years of experience in the Netlink interfacing to the objects. There's a lot of expertise that has been built over years. We don't want to reinvent any of that. So we're just putting the objects are only accessible through Netlink, not through eBPF. eBPF is only responsibility is to compute the data path in software. That's about it. If you decide you don't want to do anything in the software data path, then these packets will never show up in the software. They use this as purely a control plane. More than likely, you may need to split your pipeline into hardware and software, etc. So your mileage may vary. I can take questions of this if there's any, or I can move to the next slide. Okay, I'm gonna assume I should move to the next slide. So this is, now I'm going to lead towards the control plane API, which is where OPI would fit. This is just a detail of how we build the headers from user space towards the kernel. But the most important is using Netlink. It's a very fixed API that should never ever change, regardless of the P4 program or your data path definition. So this is static. We upstream it once and we're done. Our API from the control plane is more sort of, it's not gRPC equivalent, it's more CRUD API, right? Actually CRUD plus publish plus subscribe. So it's CRUD plus publish plus subscribe. So you have a verb. When you send the command from the control plane, you specify a verb. This example here is shown get, but that's actually a read in the R there. That's that read. You specify a noun, which is a path to the object. In this case, we're pointing to an entry which had on this table called my table, an IP address which can be described for humans as an IP address of this format. What this thing does is it consults the introspection file in order to construct the semantics, the binary semantics of this PC. So it's basically verb, noun, and optional data. Sorry, somebody had a comment or a question. I had some sound.
Jamal, I have a question. This is sort of it seems like a good fit native backend control plane interface. Have you thought about marrying this or reconciling it with either TDI or the official P4 runtime, which is gRPC based? Have you thought of the relationship in those?
Absolutely, there is a relationship. So I'm going to show that in the next slide, I think.
Great, thank you.
Right. But there is, so essentially just think of CRUD with publish plus subscribe. So I mean, this is the most common term, but we would like to say it's CRUD PS, or it's CRUD plus implicit subscribe and report from the kernel. For example, I can subscribe to an event so that when I create an entry like so. So actually, let me focus a little bit on this. There's a verb followed by a noun, optionally followed by data. So if I'm doing a create, I'll probably have data. If I'm doing a delete, I don't have the data. If I'm doing a read, I don't have to specify the data. If I'm doing a subscribe, I may have a filter data to follow, right? So this fit very nicely with just a handful, 4, 5, 6 APIs that look exactly like this. I could have a read, or I could have one function called runtime, read, comma, noun, comma, data, right? For sorry, comma, there is no data here. I'm sorry. I'm just read, comma, noun. That's it. And then I get back my object. The path could also be shortened, so I don't have to specify an explicit entry in the table. I could just specify the whole table. So in this case, I'm dumping the whole table. So if I have a million entries come back from the kernel. I could create a single entry. This is where first time you're seeing data here. I've specified the create command, the path to the object, which is going to be a key of that sort. This is just for human readability. What goes on the wire is a binary representation of that. A priority, given this is an some sort of pseudo LPM / ternary. And the data is to saying, if you match this at priority 16, then I want it to drop, right? Or I could batch. So these are the kind of things that I said are experiences that we learned from over the many years of TC Flower, for example. This kind of semantics are a little tricky to do there. So instead, I could batch a whole entry as much as my socket buffer would take. I could batch many entries at a time, and I could delete many entries at a time, or I could flash the whole table. So if I say delete, and I just specify the table, then that's a single message to delete everything in the kernel, that whether it's offloaded or not. So leaning to, I think, what Chris was asking here. So we have an underlying API. You see about 6 commands. on top of it, this is what I was referring to, is the TCCLI, which is where we're upstreaming this generated introspection file. You essentially, if you want to call it a chicken peck or a hen peck, every time there's a human types on the command line something, you go and query the introspection. So yep, that's accepted. He means 10.10.10.10 is an accepted command. It's actually a 32-bit network order set. And if essentially you call this handful of netlink commands, and you could either send it to hardware only, hardware and software, or best effort, we say put it on hardware. If it fails, go to software. So this I call the generic because they require the introspection file that the compiler generates. However, you could, so to answer your question, Chris, you see TDI is there. I forgot to put P4 Runtime, but P4 Runtime will be one of the consumers of this API. Right, so you could go from remote, come all the way here, and just call one of these 6 commands. And this should be sufficient unless we're missing something that's to cover everything that P4 Runtime would need.
So these blocks called TDI, are these aspirational or have they actually been implemented?
The Intel people may be able to respond to that, but I think, yes, they are looking at this. Absolutely. Okay. Right. I don't know if I say too much there. Is any Intel person here that can respond to that? But yes, they are definitely looking at these. I don't have P4 Runtime here, but there's nothing stopping someone from writing a backend to P4 Runtime to invoke these APIs.
Yeah. I co-chair the P4 API working group, and tomorrow we're meeting to talk about a generic tables initiative that Intel has been spearheading for some months. They actually spoke about it at the P4 workshop. So I want to bring this up because probably some of the same people. And I'll see if there's any connection.
I'm sure there's an intersection of people that are looking from our side as well.
But I like what I'm seeing.
Yeah. So the other thing that has been slightly of a failure, let's say with Flower, is the performance perspective of how many entries you can add. What is the latency is probably the most important than throughput. Throughput is probably, like if you look at container workloads, a container comes up and goes. So you probably will add 1 or 2 entries, but you want to add it very fast so that it doesn't it doesn't consume a big chunk of a short lifespan for a container. If a container is only going to last 1 second and you're spending 1 millisecond updating, then that's probably, you're slowing down the container from spinning up because you're updating a table entry in the hardware. So we are still spending a lot of time. I don't have exact numbers today, but our goals are in that range. So if I was, for example, to batch, that's very easy to achieve. But we're also looking at individual entry latency and throughput, right? So I'm just going to keep adding only 1. I'm only going to send 1 entry from the control plane and see how fast I can do those over as little CPU, and you scale it by adding more cores if you need to, right? Because some of the hardware that we've seen is extremely efficient in doing a lot of batching, but may not be very good at doing individual entries. So we're doing a lot of performance analysis on this. Status, we are still, there's an ongoing effort to upstream to the Linux kernel. We haven't posted any of the patches to IP Route 2, but we have plenty of patches there. The last patch this year was posted yesterday. We have bi-weekly meetings, a mailing list. There are multiple vendors involved. Intel is very active doing offload. I think if you're there, Chris, you may have seen the demo from Intel at the P4 workshop. It's still work in progress. It's not production yet, but they're putting a lot of effort.
Yeah.
And last but not least, we have a website. It's not being updated really in a reasonable timeline, but we will update it. What you may end up seeing there is us talking about scriptable approaches. When we first started, we did not want this path, right? We just wanted to generate an ASCII file that I can then email to somebody and say, okay, do you have kernel 6.4? Yeah, okay. Run this script and you'll have yourself a P4 program in the kernel, and then start just using P4 Runtime or TDI, and it should just work. And if you want to offload, just toggle the offload button. So operationally, this was very simple, as opposed to you're generating an eBPF program, you're compiling. There's still a lot of immaturity in terms of eBPF with different compiler versions, different kernel versions. The verifier could go nuts on you. So we did accept eBPF to move forward to that. It does have some, in the simple cases, eBPF performs very well. This is the data we presented at the P4 workshop. In the complex cases, once you start having real programs with 10 tables, some of them being ternary, some LPM, then there's probably not much difference between an interpreted mode, which we initially had started with, and eBPF. You're just chewing the CPUs, right? Tons of cache misses. So it did slow us down. There was some pushback from the community, so we adapted and went back and implemented the eBPF stuff. So operationally, it's a little bit more complex, but it is what it is, I would say. And that's it. I can stop here. I can go into details of anything someone may have a question on.
I don't mean to be the one asking all the questions, but I'm curious if you could go back to that diagram, when you load the P4TC program, it was kind of the middle of the diagram.
Mm-hmm.
What does that code consist of? Let's say that in that load P4TC program using Netlink, what does that mean? What is the code? What is how is the pipeline implemented? Or is it just using TC constructs that are already there and you're just hooking them up?
We're building all the objects that P4 needs in the kernel. So we have tables. We have a way to prescribe an action, because if you look at TC, consider TC as a static pipeline that can be, of course, it's not a static pipeline, but it's static objects. You can only use Flower, which is one way of implementing a table. Right? Our implementation is an algorithmic TCAM in software. So
okay.
you can use it.
Okay, so you're extending the kernel to include basic building blocks that then from userland you can hook together into a P4 pipeline.
Right. So I can script how I want the pipeline to look like. Because I'm doing it from the compiler.
Yeah.
Right. I look at my P4 program and say, this is how the pipeline looks like. I'm going to generate everything the parser needs, the metadata, the pipeline itself, the actions. What are the control objects? And then I'll generate another P4 eBPF program to deal with the data path.
I guess what would make it a little more easy for people to understand at a glance is in that kernel box down there in the lower left. If you showed something maybe in green that says, these are the new widgets we've added to the kernel that let you do this.
Yeah, the blue, I'm sorry, is the only widget these are the widgets we've added. There's tables.
Oh, okay.
The green,
so that's kind of
I was
the
trying to
kernel
mark
view.
the green. I know a lot of people, this is, for someone who's new, this is kind of hard to grasp immediately, but the color coding is green is what's generated.
Right.
All the way to the hardware.
I get it. That's exciting. It reminds me of the P4 DPDK, and that there's sort of basic constructs that then when you compile your P4 program for DPDK, it kind of weaves everything together using pre-built widgets.
Yeah,
right?
I think when we started this, we were not aware of that, but it seems there's a lot of similarities. So it will be a lot more similar to what we had before, which is the scriptable version.
Mm-hmm.
Where we actually, I don't want to call it that, but we came up with an instruction set. And I think probably this is what arced some of the eBPF guys, because it's an ISA. We came up with an ISA. So, but as a scripting, because we do not want to change the kernel. I don't want to compile anything. I just want to tell the kernel, here are the instructions I want you to run in the kernel. And there are commands. We call them commands to avoid controversy. That didn't help. People caught on to it and see you got an ISA here. Right. So we removed our ISA essentially. So we are making good progress. We are hoping to be upstreaming. Right now, everything we upstream is tagged as RFC, but we're hoping to remove that tag, and then more serious discussions will happen. We are hopeful we have good hope that this is going through. The code is written in a way that it does not touch anything in the core kernel that other people are using. It's standalone code. So if you turn off one option, you're done. If you don't use it, even if you compile it in, it doesn't affect your data path or your complexity of anything you're doing. So it's very clean code.
Have any figures on like scalability, and are there any limitations, or can it implement P416 pretty faithfully?
We may be missing some objects. We're implementing as much as sometimes as on demand. We're not sure if we should implement everything. We wait sometimes for someone to ask, then we'll add it. But majority of it should be there. We're focusing more on P&A right now.
Mm-hmm.
Right, so P&A, including all the externs, etc., they'll be available. We're also working with a mechanism where you can write your own extern. Again, no need to upstream anything, and it will just work out of the box, including providing you a control plane interface to your extern.
Wow,
So,
that was my next question. And are those running in user land or kernel?
no, they'll be mostly running as kernel modules. Your choice, really.
Kernel modules. Got it.
Yes, right. And we're not sure if the compiler should be generating because there is no spec for extends, but it is feasible that if we come to a standardization for how extends should be defined, that we can generate the extend code. Not all of it, but I would say a good chunk of it. So again, one of the goals of this is we don't want experts on the kernel or eBPF to be necessary for us to deploy this.
Pretty exciting.
Thanks.
Yeah, Jamal, this is very exciting. I have a question on the actually a couple of questions on the API slide. Can you go to the CRUD APIs where you were showing the OPI synergies?
Right. Yeah.
Yeah, in here. So all these APIs, when you say path to objects, these are the objects that are defined by the user, and the data is also dynamic here and not something which is fixed as part of the API, if I'm getting it right.
That is correct. The
And
API
there,
looks close to this.
got it.
So if you do a read, this is, given that every P4 object has an ID, it makes it very easy. So it looks like a Unix path, but we're saying, it's the pipeline ID followed by the object being a table, maybe in a control block 1, my table ID number 3. Here's your key.
Right.
That key is a blob, a binary blob that gets sent.
Got it. Okay, so in this case, the part of standardization that you're looking at from this group really is if we can have these APIs as a standard way of manipulating Datapath tables, and these will be lower level APIs to do the table manipulation. That's the kind of thing I'm assuming you're looking at from OPI.
So we could essentially provide a library that has all these 6 APIs, taking arbitrary paths to different objects, which could be human readable if you're using a CLI, like you're using TC, or you write your own app, or you could write your own app that's totally compiled. It only deals with the data path. It doesn't know about anything else, right? It could be Python or whatever, maybe even generated by the compiler, right? Very specific to your application. If you're just running an L2 bridge, then it only knows is L2 bridge, right?
Got it.
And these are the APIs basically that we think are fit for OPI.
Okay. The second question I had was in the diagram that you were showing, there's practically no user component or user level component of this, which will be needed to intercept any data path function. Everything is in kernel or southbound to the NIC.
Okay, you're talking about this part here, right? This. Yeah. So we have XDP, for example, which if you want to send it to user space, then this could be replaced by AFXDP, for example. Your mileage will vary, really. Do you want to send your packets to user space, or do you want to process them in the kernel? This code is generated out of your P4 intent, right? You define your P4. That intent is codified into eBPF code for the data path. And you really don't have to pass any packets to user space if you don't want to the kernel even. If your hardware can handle everything.
Got it. Interesting. Thanks.
Yeah. More questions?
So if I understand it correctly, Jamal, we would be able to put, say, the shim layer of OPI, which would be passing down, say, gRPC to the DPU, right? And then it would just utilize these CRUD SP calls essentially underneath.
Right. So you'll
Okay.
have to translate.
Yeah, just do a translation to that. Now,
Yeah.
the varying, so from a DPU perspective, we've got multiple vendors, so we're trying to make that relatively agnostic. You would see that the SDKs or the hardware interfaces would sit down there at the very bottom of the data path. Is that correct?
That would be a driver from the
Right.
vendor.
Right.
Right.
Okay. Okay.
Right.
I just wanted to make sure it's clear in my head from looking through this and listening to the presentations. Okay, I got it.
And
Right,
Jamal,
so-
is either any of the interfaces like this already implemented in the Netlink itself, or this is part of this work?
Typically in Netlink, most people will just create a TC interface, right? So then this is hidden inside TC in IP route 2. But we are going to make a library release that just provides this API that TC could use. Right now, we are integrating into TC. So if you have to study the TC code, you have all these APIs. All right. So it's currently integrated strongly into TC, but our goal is to remove it out of TC and make TC just link it in if it needs.
Because we have several implementations in OPI already that translates from gRPC to Netlink, and we're using Go Netlink library, and I haven't seen any of those constructs in the Netlink Go library that we're using.
Yeah. So unfortunately, Netlink has deviated from its origins, but these were the origins of Netlink, really, what I'm showing there. The other thing with gRPC is, if I was to show you this, see how our semantic looks like? This is the API semantic, essentially, and the wire semantic as well. I have a verb followed by nouns. Nouns are, I could have millions of nouns, followed by optional data, which is tied to the noun. The gRPC tends to converge verb and noun into one thing, right? So you say add foo, and here we're saying add space foo. So you would have
but in the gRPC, in the protobuf definitions, we have the resource ID and full resource name, which is translated to the noun. So I see how we can easily translate between the protobufs and the TC here.
You should be able to take protobuf, separate, disambiguate the noun and the verb, and then just use this. If it was a create, doesn't matter if you're creating an MPLS object or a routing object, you just separate it, you call create, and you give it the path. Now the path itself is, so P4 has an ID for every object and hierarchies of objects. So I can specify to a table. I can go all the way from the pipeline and say that pipeline number 3, without giving names, names only for humans. Table number 4. Here's a binary blob that the kernel will then verify this, is this legit for this specific table. If it is, then we will go and use it as a key to retrieve the table entry. So the difference, I guess, is the separation of concerns verbs outside of nouns. That's why it's so easy to have only a few commands instead of many commands. The other piece basically sits in the data, in the API itself.
Makes sense.
Yeah, I'm not sure I totally agree with the statement that gRPC typically has commands like set foo or get foo. I think it just depends on which domain you're in, and, the style. Like many of them are generic like this, get or set, and then a list of, paths like GNMI, for example. So I think what you're doing is well proven path.
Yeah, the challenge is I think if you look at protobufs, they are kind of defined, whatever the service or message, I think they call it. They kind of defined to construct a noun with the verb.
Not everywhere. I agree with Chris that if you take, for example, OpenConfig with GNMI, GNOI, they just have a very similar abstract construct, and then inside the data you can put whatever you want. So it doesn't really specifies all the details that usually protobufs do. So that's a known hack that
Okay.
people already.
P4 runtime's the same, right? So this is a good fit actually for better practices, in my opinion. I like this.
Yeah, it's a lot easier to have just a few verbs. Yeah, I think the keyword maybe is it's a hack, right, on gRPC or protobuf. It was not initial design consideration. Now I come from a world of where we implemented something called forces. I don't know if you guys have heard of it, but I guess every few years the same fashions come back. So back in those days it was Network Processor Forum. I don't know who's participated in Network Processor Forum here, but the forces came out of the Network Processor Forum, which was trying to standardize the NPUs that came up in those days. Right, so how do you talk to them consistently? And this semantic that I'm describing here has its origins in those days. But also this is how RESTful APIs will probably work, right? Or HTTP verbs versus URIs.
So all those APIs that you're currently listing here is, you said you're going to create a library that TC-CLI and other applications can actually either compile with, import, whatever, and use those libraries. Is it going to be part of, like, where you're looking for hosting this library? Is it something expectation part of the OPI project GitHub organization, or you're going to post it on your GitHub with a P4TC?
So our original intent is we're going to push it as part of IP Route 2. The library will be part of, if the maintainers of IP Route 2 would like that. But we're going to rewrite our TC code right now because we're in deep development, so we didn't bother to separate it out. But we're going to rewrite the TC CLI to link to that library. And then that library, if it's public, it's just a package that could be delivered as part of a distro from a vendor. I mean, like
that I understand, but you're looking to host this library separately as a standalone project as part of what GitHub organization?
Unclear at this point.
P4TC
We're just going to
IP
make it part of IP Route 2. Yeah, we're going to initially our goal is to make it part of IP Route 2. So you just pull in IP Route 2 and you have it. But that we haven't had that discussion with some of these maintainers.
Yeah.
If they
So
push
from
back,
OPI perspective, going back to OPI perspective, you expect us to consume this library as well, right? As a consumer, or
yes. So you would have, if it's your app or your app here, which consumes the introspection file from the compiler. This is a little slow because you keep checking with the introspection file for validity and human translation. But you could generally take, I should be able to take that description that the compiler generated and create a specific appliance / binary for it, for my code. And it will use that library in that case. So you don't need to use TC in order to take advantage of P4TC.
Interesting.
So the only thing that will be standardized, if there's an API, this is how the API would look like. Right, I think this would be a fit for OPI, but I know there's other, you guys have had discussions for a while now, so you may have thought of something different. Like if you're using gRPC, then your spec is maybe the protobuf. And we're saying we start with P4. That's the mother of all languages for Datapath. And we can generate an introspection file which defines, this is a JSON file. I wish I had an example to show you right now, but
yeah. The reasoning that I'm asking is obviously not all vendors support P4 in OPI. So what we thought about is we are going to do the gRPC, then we're going to translate it to either P4 or something else, like maybe RT flow with DPDK or something like that. Right. So for those who are using P4, this abstraction layer is the translation that we're going to use. So we are agnostic to vendor-specific P4 stuff, and this API is actually useful. This is my initial thought once I see this.
Makes sense, because you've got to cut off a lot of different approaches. The only challenge would be, so we're trying to avoid levels of interaction, right? So I'm going to listen to events here, and then I'm going to have an abstraction layer that will translate depending on the vendor, or it may go gRPC one way or another, or something proprietary.
Yeah, this
But
will
I hear what you're saying.
definitely creates an abstract. Yeah, this is creates another interaction. You are absolutely right. I hear you. Yeah.
So Jamal, do you see a future where a variety of DPUs can do hardware offload of this?
Yes, that's the goal. I mean, Intel is taking the lead, but we're talking to other vendors. Maybe I shouldn't say anything, but if you show up to our meetings, you'll see vendors.
Yeah, I wasn't asking to reveal anything here, but just
No, I
feel
mean,
like this could actually, in a way, this sort of is like a retake on earlier efforts some years ago of vendors trying to offload
yes.
P4 or eBPF on their NPUs. And it seems like, technology has advanced quite a bit since then. So maybe this is like the second shot at it.
It's a second shot. You're right. It's like bell bottoms are coming back or something. I don't know what people wore in the 60s.
Yeah, groovy, man.
Yeah, it's groovy now. All the cats are coming back.
Yeah.
There's nothing new here. This is control data path separation, well-known patterns. So the one thing that P4 doesn't prescribe, by the way, is the event stuff that I can subscribe to be told when a table gets changed, for example, or an entry gets deleted. That's this subscribe thing here.
Yeah. P4 Runtime has, a control channel, like a stream channel for digest and things like that, packet IO. So
Yeah,
there's no reason why it couldn't be extended to handle arbitrary events, right?
Yeah, so the digest we will support. It's not here because it's part of essentially it hooks up. It's going to be code that's generated for digest. So you don't need to do any control interfacing for it. It's your P4 program that needs to deal with it.
Do you have a guesstimate of when this might make it into the kernels?
We're getting close. See, we had the code ready to go, but there was that religious debate, and we added eBPF. Essentially, we added this piece here that did not exist before this. This was ready to go. It was working. Offload was fine. And the one advantage I can tell you is, for example, for extents, you can write it in Rust. You don't have to write it in eBPF at all.
Yeah.
Right. So there's a lot of language fans for Rust as well. So we allow for that.
What I like about this is it provides a sort of a 2 tiers of performance, right? You can do it in pure software, prove the design, and then if and when there's hardware offload availability, that could get a big scale increase.
Exactly. You could build digital twins in pure software if you wanted, right? So there's a lot of use cases. It would be a good replacement for BMV2. I don't know where that thing is being developed anymore, but I can test this on Mininet, for example, if people are familiar with that, or I can build a whole cloud-based infrastructure of how my distributed P4 program is going to run.
No, this
prove it there, and then go and offload it to real hardware.
Well, even in a pure software mode, this is extremely interesting for cloud applications done in software.
Yeah, we really don't want to sort of get some people upset that this could be competition in some cases to eBPF as itself, because eBPF is just in container workloads, for example. Right, you have to keep writing your CNI and you're hard coding your eBPF code, whereas I could just generate what I want for my use cases. And I just have a new CNI that just works for me. I don't care if it doesn't work for somebody else.
eBPF code is not that easy to write.
Yeah, so it's better to have a machine generated as necessary.
Yeah.
we're still struggling with it. So I think the one thing that gave us good leverage is the fact that now we could call this kernel code. So we don't have to wrestle with the verifiers much anymore. And we could take advantage of the fact that we have Netlink running here, which is very well proven control plane API, without having to invent something new on top of this. That is something we have tried. It's just not, you can't ignore the many years of experience of fixing the corner cases in Netlink. Instead of inventing them here, we're just going to continue to use this. And the fact that the P4TC already handles offloads, which we're just reusing. We're really reusing the callbacks that exist already in the drivers.
Thanks, Amal. I think, as P4 vendors, this looks very exciting to AMD for sure, but and also bringing P4 to the mainstream. Having said that, Boris's concern is equally valid as to this could be used by P4 vendors who are implementing P4 natively quite well, and not just prototype P4 code, but also take it to 2 stages and implement prototype and then accelerate when you have the right hardware. But more importantly, how do other vendors use this API who are not implementing P4 to take advantage of it? I know this is not the main charter you have, but what are your thoughts on, is there any way to have other vendors also take advantage of this? This is, again, I'm not speaking with AMD hat, I'm speaking from the OPI side.
So by the way, I agree with that sentiment that you may want to cater for a lot of other approaches, because you're in the business of advancing network programmability, and maybe P4 is not the only game in town. It just makes it very easy to, P4 just simplifies things. I don't have to worry about, right?
So, no, from my point of view, it greatly simplifies and make it fully mainstream. Absolutely, yes.
Yes.
Having said that, I'm just saying that, is there any way this can hook into something which is non-P4? I doubt it, but maybe you can.
Actually, what's funny is when we just last week, we created a program that replaces the Linux bridge with 1 page of P4. Right, it's to test our stateful. I'm not saying it replaces 100% of Linux bridge, but this classical. I may even have a diagram here. Let me see, of how the P4 program operates. If I'm lucky, I'll have it somewhere here. Maybe no. No, I don't have it here. But it replaces basically the. Oh, there it is. Okay. Here's a P4 program that replaces a good chunk of the Linux bridge. You basically have an FDB, which can be looked up by, in this simple case is just showing by destination mark, but I could add to the key the VLAN. I think we have an example now. We've morphed this to be something that takes both, can be told to take either VLAN or use VLAN 0 by default. And it is also does learning, right? So the add and miss works for PNA. And the point I'm trying to make is we could take this program, compile out P4 Linux bridging in the code, in the kernel, and then be able to use the FDB offloads that exist in a driver. So I could take this on something that's absolutely not aware of P4 and use it for layer 2 bridging, because a lot of vendors do offload L2, like they offload the FDB mostly for virtual machines and stuff like that. So it is feasible that I could still specify my spec. I could still consume as a non-P4 piece of hardware, and I'm not talking about OPI here, but in general, I would ship my customer a P4 program which they compile, or I just ship them a binary which conforms to this API, and it just works. Right. So this would run on a very old Intel piece of hardware called the IXGBE. I don't know how many people have used that, the 500 series. It will work just fine there, and it will offload. And that I can tell you that the hardware has no knowledge of what P4 is. I'm not sure if I'm answering the question, but I may have gone on a tangent a little.
Thanks.
Pippin, you're concerned about APIs. Would using TDI as a common abstraction be an approach to mitigate that concern?
TDI is again, to me, is more of a P4 thing, and it works great for, like I said, any P4 platform, including AMD. But I think my question was a bit broader. How do we get? What's the answer for people who are not implementing P4? That's where I was trying to go to. So TDI is great for P4 backends.
I think TDI is good for anything that can conform to a logical table, right? You could map onto a tomahawk just as well.
Yeah.
So
I see. So you're taking TDI as a generic way of manipulating match action logic, could be used with P4 or not P4 OVS or something.
Yeah, anything you can map onto a two-dimensional table basically can be done through TDI. It doesn't have to be P4 based.
Or anything you can squeeze as a table. You could have just one atomic variable that is a table with one entry, one column.
You can do it.
Yeah, no, that's interesting thought. I was always thinking TDI in the P4 context, but certainly we need some adaptation from that into what exists in otherwise non-P4 systems. Makes sense. Okay, thanks.
Okay, we are at the top of the hour. Jamal, thank you so much. If it's possible, if you can share the slides out onto the Slack channel, we can also upload them.
No problem. I'll send them to you, and
that'll work.
Thanks. If you have any questions, please reach out to me.
We will do that.
Yeah.
Thank you.
All right. Thank you very much.
Thanks a lot.
Thank you. Bye.